All right, so today's topic is on big data and PySpark. I think I've sort of mentioned a little offhand, big data and PySpark as a topic is quite separate from the rest of the phase. It's something that's like a good introduction to big data. If big data is something you want to pursue, big data, I would say, is quite different from data science. You know, all of the projects that we're going to be working on within data science are all, set data sets that we can run on our Jupyter notebooks, run on our local machines. And that is like not big data. Big data, as I'll get into, is like not even millions, but you're talking about like terabytes of data. And so even though the way that you treat the data is going to be quite similar to, how we treat smaller data sets, you have to work on different kinds of software, different platforms that are able to handle this big data. And we'll talk about some of the concepts involved in like, how what we're doing on our current data sets can be scaled to big data. But yeah, so that's big data. PySpark is it's a software developed for us to use Python to work with big data. In your lessons, there are some lessons that outline how you can download Docker to work with PySpark and basically work on machine learning tasks. You'll be doing a bit of data cleaning in some of those lessons. I believe one of them has you like run machine learning models. So you can do all of the same stuff that you're doing here. All of like your pandas data frame stuff, all of your scikit-learn stuff, the stuff that you're doing in your Jupyter notebooks locally, you can scale it to do that on big data with PySpark. So a lot of the PySpark like commands that I'll just like walk through a couple of them towards the end of this presentation, just to show that there's very, very similar functionality. It's just the scale of the data that we're working on is going to be different. Just as a quick overview, we're gonna do an overview of big data, how big data is defined, and like where's the delineation between like regular data sets versus big data sets. I would say a very, very important concept to just be aware of is Mapreduce and distributed systems. So I'll be talking about that as well. There is the Hadoop ecosystem. Hadoop is a platform that lets you work with big data. And then we'll be going into Spark and PySpark. This material is actually quite similar to the readings that you have at the start of this section. So you can see here Spark and PySpark, we have Spark context, yada, yada, yada. All the same stuff is here. You have PySpark, Spark context, distributed data sets. So it's just going to be an overview of what you're going to see in those readings. Any questions before we dive into it? I actually have one more slide that's like kind of an overview, so I want to do that first. This is what you won't be able to do after like going through all the material on this topic. So Mapreduce, as we'll see later, is actually written in Java. You will not be able to do that just because we don't know Java. It takes a very long time to become proficient in end-to-end ETL, and ETL stands for extract, transform, load, which is a big part of data processing. You won't be able to do that in Hadoop after like 1 day's worth of work. There are data engineering courses that go through that material, and I will send those links out probably around capstone time as you guys decide which direction you want to go off on. You also won't be able to work with AWS instances, and we'll get into AWS. Probably I'll talk briefly about it during capstone, but yeah, AWS allows you to productionalize your models. If you want to like host them on a web app, you can do that with AWS. And if you want to set up web apps that work with big data, AWS has those products that you can use. And it's really up to your company what platform they choose to use. And just as like a quick caveat to this entire topic, all of the frameworks that involve Mapreduce, Docker, PySpark, and distributed systems in general, they're very, very technical and specialized. People spend like, I would say like 6 to 12 months learning all of this stuff. If you want to be like a big data engineer, it will take, I believe, another course on top of this to become proficient in big data. I will say, very, very rare. I don't think none of my own students, I'm not sure about others, but very rarely you have someone that comes out of this bootcamp going straight into working with big data, just because the platforms are very different. I would say only after you are very comfortable with programming, and by that I don't mean like running models, but I mean like actually, you know, learning, debugging, being very proficient with not just Python, but just languages in general. Again, because different platforms use different languages. Only then will you be able to, I think, successfully break into big data. So I want to set that expectation for everybody. So we're only going to talk about it in on a high level. Questions or thoughts about this? All right, let's get into it. So really quickly, big data. What is big data? It's characterized by three things: volume, velocity, and variety. So big data is big in these three ways. So first, volume, right? We're talking about like terabytes of data, just a huge amount of data that is going to take a very, very long time to process on a single machine, which is why later we're going to talk about distributed systems. So just the size of data is one of the big components of big data. Then you have velocity. Velocity, like speed, you have to think about big data is constantly being generated. You're constantly going to be receiving new pieces of information. So you have to have an architecture that is set up to process information as it comes in. That's one way to do it. Or have some sort of architecture set up to like hold your information before it is processed, and then have it go through processing steps. So again, it really depends company by company how that is set up. But velocity, which is really just the fact that data is continuously streaming in, that is another component that makes big data big data. And then finally, you have variety. So the kinds of data that we're working with so far, it's only been like, you know, I feel like the most common data types that we've seen are like just CSVs, JSON, stuff that comes from APIs, numerical, maybe there's strings. Later this phase, we'll be talking about images. But yeah, you imagine how much unstructured data there is out there, things that don't exist in, you know, in a table format. So here you can see that they have like photos, web pages, audio, video, things that are unstructured. So maybe they have like varying lengths of audio recordings. You can imagine, I don't know what kind of information our like smart home devices are collecting, but that is very largely unstructured. So they're not in a table format. So the fact is that you think of these big companies and what kind of data they're collecting, it exists in many different forms. And so yeah, big data just has these three main components of which, you know, you characterize big data as big data because of these three growing components. Questions about this? All right, well, it differs from the data that we're used to working with, because the data that we have, I mean, the fact that we can open a CSV file on our computers means that volume-wise, it's decent. We don't have continuously updating data for CSV files. And often when we're looking at the data that we've been looking at so far throughout this course is usually in like maximum 1 or 2 different formats that you get to synthesize. It's a lot easier to synthesize when you only have like 2, maybe 3 different formats. So just imagine like the kind of like data processing pipelines that people have when you have audio data, image data, video, when you have like, let's say you have like a dictionary format of like people's information, stuff like that. All right, so distributed systems, and we'll get into like what that looks like and how that works. But why do we need distributed systems first off? This is just some like quick math, and this is really just a hypothetical example. How long would it take for 1 terabyte of data to be read on a hard drive? And this is just reading the data. So imagine doing like a pd.read CSV. If you have 1 terabyte of data, it would take roughly 3 hours for your computer to just read the CSV. I think the biggest CSV that I've ever looked at was about 7 million rows. And that was not even, that was, I think, less than 20 megabytes. And that itself already took, a full 2 minutes to open on my computer. If you have it on a distributed system, and you can sort of think of a distributed system as like computers running in parallel, same speed across 10 systems, you have 105 seconds. Yeah, and these are the different speeds. So at 100 megabytes per second, you have, oh, I guess I should have used more constant speeds, but anyways, it would be faster if you had 10 computers reading your data versus just one. And we'll talk about how, what is the structure that is set up that allows 10 different computers to work on the same task. All right, so that's just, I feel like pretty straightforward. If you want something done faster, get more people to work on it, or get more machines to work on it. All right, so let's talk about distributed systems, and that's what Hadoop is. The next slide I actually show like where Hadoop and like Spark fits into like the bigger picture of dealing with big data. But Hadoop is a distributed, it's a company that built this distributed computing system. It also is an environment that helps computer clusters work on very, very large data sets. So basically, the client is you. And what you do is, if you want to, like, for example, let's see, as an example, you just want to like count the number of words per article that exists in every article ever published in the world. You would tell it to do that on the master node, and Hadoop is a system that includes the process of splitting up the work amongst, for example, 3 different computers here. And you can see these are called the master node that gives its jobs to slave nodes. Each slave node will work on its own tasks, and then there's a process of re-aggregating all of that information back together. And so Hadoop is the part of the, Hadoop is responsible for that part of the process. Hadoop, as well as in the next slide, you'll see Hadoop and Yarn are in charge of, the architecture of that, being able to take your work and split it across multiple systems and re-aggregating that back. Questions about this? And there are a lot of different variations of this image that we're actually going to see in this presentation, just because different companies can set up their systems slightly differently. But in a nutshell, they're all using this like split up my work and then re-aggregate. Oh, and the elephant, that's the logo of Hadoop. It's not just like random elephants that I put on the slide. All right, so the Hadoop ecosystem consists of a lot of different things. So these are just definitions. So here you can see at the base level, we have HDFS, and HDFS is our Hadoop distributed file system. Again, like I mentioned earlier, is what allows us to distribute our data across a cluster of computers, making multiple hard drives in our cluster function like a singular file system. So again, it's that process of being able to split your data up and re-aggregate it. And so us working from our perspective, we're not recognizing that it's done across 10 different computers. It looks like it's all happening at the same time, but it's just all of that splitting and re-aggregating is happening within Hadoop. On top of Hadoop, there is Yarn. Yarn is, I feel like, not talked about too much, but it's in this diagram, so I wanted to mention it. Yarn stands for Yet Another Resource Negotiator, which is a great acronym, but basically it deals with the data processing. Yarn is the part that actually decides what each slave node runs and when. So it's the one that's in charge of delegating the tasks to the different computers. So some people like to think of that as the executive because you're delegating, and it is also the heartbeat that keeps the cluster running. So other resources like Mapreduce, like PySpark that we're going to talk about as well, are built on top of Yarn, because you imagine like, all right, if I have like a process that I want to be done on my data, it has to go through this, delegator, and then going through this system for it to all get done.
Wait, Ish?
Yeah.
So I have a dumb question. So for Hadoop, how it distributes it across like a cluster of computers, I don't understand how Like, do you have to have multiple computers for it to work? Or like, where are the computers?
That's a great
What
question.
computers?
That's a great question. So I know that when you're working on, if you're working on PySpark, and I am honestly not an expert in this either, but I know that like when we're working in PySpark, it's basically utilizing different servers in parallel. So
Okay.
when we're using Docker and PySpark, which is what you set up, you are basically going to split your work across different servers. And what servers means, honestly, I'm not too sure either. Part of me thinks it's like those giant boxes with like the blinking lights in like those movies, but basically that's what it is. It's like the HDFS is, yeah, it is physically different computers. I know on your computer, it's actually kind of similar to, in some of the algorithms that we talked about last phase, there was the n jobs hyperparameter that basically said like how many of like my computer's cores to use in like processing this, in like working on this algorithm. So it's kind of similar to that. If your n jobs equal to 1, it means that you're using one of your processors. If you're doing n jobs equal to 2, it uses 2.
Okay.
So in where the similarity is there, this like Mapreduce system that we're going to talk about next allows you to use, let's say you have like 4 cores on your computer, it'll use those 4 cores, it'll like split up your data across the 4 cores, so they're running in parallel. And so technically your process will run 4 times quicker.
Okay.
But it's literally like, yeah, the physical hardware that is being like it's distributed across different parts of the hardware.
Okay, got it.
Yeah, if anyone is an expert in like computer hardware, let me know. And if anyone has like an answer, also please let me know. But that's how I understand it. Yeah. All right.
And when you use cloud computing, you're literally using computers at like a server center that Amazon owns. And so that is like, for me, an easier way of thinking of distributed computer processing.
That makes sense.
Computers elsewhere doing it, but that's different than like if you're doing it locally, correct?
Yes, that's exactly right. Yeah, and we'll like briefly talk about working on the cloud. Actually, when it comes to image processing, Google has its own cloud that is actually free for us to use. So I'll be introducing that later as well. Literally, I think not next week, but the week after. But yeah, Amazon is, of course, the biggest like cloud systems provider. And with Amazon, you imagine that like, let's say I wanted to do a machine learning process on big data, or not even on big data. Let's say I had like just a very large data set that my own computer can't handle. You can actually run it on, Amazon has their own version of a Jupyter notebook, which is pretty cool. And you can run it on Amazon's version of a Jupyter notebook using their servers or their computers, which you can actually pick, I think, different speeds. I think like past a certain speed you would have to pay, or past a certain like memory level you'd have to pay. That's cool. But yeah, within that you can also tell Amazon, all right, I want to take my work and I want to run it even faster. You can use more of their processors to do it. But yeah, really it's about speeding up the process and also making these things more efficient. Okay. Awesome. It is pretty tough to understand. I highly recommend that if y'all are interested in not just big data, but also like cloud computing, which is kind of related. They're kind of related to each other because if you have big data, you likely would be using a cloud service. There are a couple like courses by Amazon that I'll send links out to. I think the first 1 or 2 are free, and then after which you have to pay. I've tried going through those courses. Honestly, not my cup of tea because it becomes very, very like hardware technical. But if that's something that you want to do, I have links to those, and those are like, you know, you can get Amazon certified for that kind of thing too. All right, so let's talk about distributed systems and Mapreduce. So as we've sort of touched upon, instead of using just one computer to perform a task, Hadoop with Mapreduce allows tasks to be divided across multiple systems. One really quick way to put it, tasks are split into many subtasks. subtasks are solved individually. And again, depending on the task, they are recombined in some way of aggregation into a final result. So Mapreduce is the main, I guess you would call it like a technique of doing this working with distributed systems. Mapreduce is the thing that splits the tasks into subtasks and allows them to be processed in parallel. So you have the mapper phase and you have the reducer phase. And map should sound kind of familiar because remember we were working with map. It's a pandas function. It's a Python function as well that basically if you want to, let's say you want to run a function on every row of your data frame, you would use map or apply, but same idea. That's what map does. You're taking one function and you're mapping it onto multiple things. So the mapper phase transforms your data in parallel across all nodes in your computing cluster in an efficient manner. And then you have the reducer phase, which is the aggregation phase, aggregates your entire data and returns some final result. This code here, if I'm not wrong, I believe this is written in Scala. Scala, if you're interested in one, object-oriented programming, but also more like data engineering, working with big data, Scala is extremely fast. It is like sort of a middle ground between Java and Python. And PySpark is actually written, or Spark is actually written in Scala. So I believe that this is written in Scala as well. But Scala is quite difficult, I will tell you all. All right. So again, this is another version of like that diagram that we're going to see a few times. With your inputs, you're going to map these inputs. And this is before you split up. Actually, let me go to the next one first. So let's say you have these inputs. If you have, I know this is a small example, but with your inputs, you're going to split your inputs into the different systems. You're going to map whatever function it is you want to do. And in this case, we are doing a word count. So here, after splitting, we're going to map the function. For some things, there's a bit of shuffling done. And again, it really depends on what the function you're trying to do is. But sometimes there's a shuffling step just to make sure that, I don't know, for example, no overfitting, things like that. You reduce it. This is just an aggregation step, and then you aggregate it into a final result. So I would say this diagram is a general example, but this is word count using Mapreduce. And word count is actually the example that is in your lessons as well. I think they'll have you like count the words in like Macbeth or something like that using PySpark in Docker. So Mapreduce, I will say, is the most likely question you would be asked in like a big data interview, just because it is the underlying driving force of how functions are done across distributed systems. Any questions about Mapreduce? All right. So beyond Hadoop. So Hadoop, we talked about, is the structure of your different computers. Even though it speeds up processing tremendously, there's a couple problems. So first issue you can think about is batch processing for iterative algorithms. And when I think about this, you think about if I had a boosting algorithm and I wanted to train that on Hadoop. Boosting algorithms are done sequentially, right? So would it be much faster if I were to do a boosting algorithm using Hadoop, right? You might say it kind of, I guess, now that I'm thinking of it, kind of could work like cross-validation, but your final model, you imagine how would that work with Hadoop? Because you're basically training 5 different models in parallel. They all have different sets of data. How would that be much faster than working on one single system? And then also Hadoop jobs are actually written in Java, which can be painful and error prone without expertise, making it less accessible. So Java is actually one of the harder programming languages to learn. I've tried learning Java. It's not easy. A lot of syntax involved, a lot of semicolons and curly brackets. But yeah, Hadoop is written in Java, which there are actually like Hadoop engineers that specifically their job is to debug things that are going on in Hadoop.
So for because this splits things up into like parallel processes, then it's harder when you have like sequential algorithms because you can't like make the, I don't know.
Yeah,
you can't like intuitively parallelize that.
Yeah, exactly. Like you think about when we had all of our ensemble methods, we had the bagging algorithms like random forest that literally you're running, you can literally like build a decision tree, let's say on 100 computers, one decision tree per computer. All you have to do is just aggregate those results versus something like XGBoost or like AdaBoost, gradient boosting. You need the result from one to make the next tree. So
Okay.
Yep, that's right. So yeah, I was gonna say something else about Java. Oh, right, by Hadoop jobs. Hadoop jobs written in Java, what that means is like, let's say a function for, let's say you wanna create a function for word count in Hadoop and that doesn't yet exist. And of course you'll be using Mapreduce for that. But the way that, when you're working on distributed systems, something that's very important is the way that you re-aggregate all that information. So like, how do you get from this to this to this? Something like word count may be a little easier, but let's say you wanted to do I don't know, let's say you want to do something that like the things are more dependent on each other. You can imagine the aggregation step is much harder and people have to code that out. And so for like specific methods that are more complicated than this, you can imagine like if you want to do something in Hadoop that doesn't already exist, it's going to be a lot harder to do so. Rather than like compared to like something in Python, let's say we just wanted to write a function to print all of our metrics at once. That's something that's pretty easy to do. Something like this may be a little harder. I don't know, but yeah. Any questions before we move on to Spark? All right, so Spark is something, as we saw here, let me go back to this. Spark is something that's actually built on top of Hadoop, and Spark actually helps to make Hadoop a little bit more efficient. So back to Spark. Spark, you can see here, this is just a runtime comparison for the same task. You can see that with more iterations, the amount of time that it takes to run on Spark increases a lot less than it does on Hadoop. So we'll get into why that is. Spark is more fault tolerant. The error messages that come out in Spark are more similar to the error messages that we get in Python. It has a very high level query language that you can basically implement SQL-like semantics on top of Mapreduce. So Java, as I mentioned, the syntax is very, very complicated. You would have to write like lines of code just to, I don't know, return the first row of a data frame. Spark, as you'll see, I'll have some examples later on, works very, very similar to like pandas and like our Python methods that we're used to. Very useful for iterative algorithms. And also Spark jobs can be up to 100 times faster than traditional Mapreduce. So basically what happens is Spark has all of these efficiency algorithms that are built per groups of tasks or per task, such that it knows that, all right, if I'm doing, let's say task A, this would be the most efficient way to re-aggregate everything. So Spark is a little bit more, I guess, intuitive in that sense, where it's not just, following rules that were predefined. I guess it is also predefined, but Spark is more optimized than just using Hadoop. All right, so PySpark, which is you can sort of think of PySpark as a Python subset of Spark. So Spark, Apache Spark, and Apache Spark is Spark, is written in Scala. As I mentioned, Scala is an object-oriented programming language that's kind of like between Python and Java. And Spark is a general purpose data processing software that offers high-level APIs written in Scala, Java, R, and Python. And so you can actually use Spark directly with Python, but it's not as intuitive as if you were to use PySpark. So to support Python with Spark, the Apache Spark community actually released PySpark, which uses a similar computation speed and power as Scala, and also PySpark's APIs, or all of their methods, are very, very similar to pandas and scikit-learn. So any like clarifying questions on like, the hierarchy of all of these things so far? All right, so just to recap, Spark can be built on top of Hadoop. So you use Spark to speed up Hadoop. And PySpark is just the Python version of Spark that most Python users use. All right, so a little bit more information here. So to use PySpark, you got to use Spark context. And Spark context is like an entry point into the world of Spark via Python, very similar to how we were connecting to our SQL databases with that cursor. So you'd have to you have to spin up your Spark context first before you can work with PySpark. And I won't go through this now, but in your lessons, it actually goes through the steps of setting up your Spark context. And so resilient distributed data sets are the fundamental data structures of Spark. I like to think of it as the pandas of Spark. So RDDs are essentially the Spark representation of a set of data spread across multiple machines, and your APIs allow you to act on it. By APIs, I really just mean like the methods. So yeah, RDDs are to PySpark what pandas data frames are to Jupyter notebooks. Later, I think I think I do have an image somewhere in here, but with an RDD, it will look just like a pandas data frame. The fact that it is split up across multiple systems is not apparent to us as a user, but you can assume that that's what it's doing. It is what it's doing in the backend. It is doing that. It is splitting up the data across different systems for you. So yeah, RDDs, just like with pandas, how you can read CSV, you can read from Excel, you can read from HTML and JSON. Very similarly, you can read RDDs from text files, databases, JSONs, etc., even CSVs too. So basically, RDD is the PySpark version of a data frame. So features of RDDs, and RDDs stand for resilient distributed datasets. RDDs are resilient. It has the ability to withstand failures. If you hit an error message, it won't, it won't it won't compile your errors. It is also distributed. As I mentioned, the whole purpose of like big data and Mapreduce is that it spans across multiple machines. And they are data sets. They can come from any sort of data type, just like with pandas, as long as you can manipulate the data into a table format, it can exist in an RDD. So creating and working with an RDD, with the Spark context, and I guess I'll go through like really quickly what this looks like. Here you can see from PySpark, you can actually get a Spark session very, very similar to when you're setting up your cursor for SQL. Once you have your Spark session here, what we're doing here is we're parallelizing this data set, this 1, 2, 3 ABC up to like 7, 8, 9 GHI. This is our data set, our RDD. So we're going to parallelize that, turn that into a data frame. And let me wait for that to go away. That table at the bottom, that is what we see as users. So this is literally a data frame, but this is an RDD because this is parallelized. This has been parallelized, which means that this data has already been split to, I guess in this case, 3 different systems. Questions about this? All right. Oops. So after you parallelize your data, you can then work with your external data. So with RDDs, you can either interact with files that are in your Hadoop distributed file system. Maybe you have objects in your Amazon S3 bucket. I realize that we haven't talked about that yet. Basically, if you have like a big data file that you don't want to keep on your computer, you can actually upload it onto Amazon in what is called an S3 bucket. And basically, that's how a lot of companies host data or host web pages in something called an S3 bucket. And an S3 bucket basically acts as like your folder in the cloud that you can store data in. So you can basically access whatever files in your S3 bucket using Spark as well. And also, as the example that you will work in your lessons, you can also work with lines in a text file and pretty much any data file. All right, so Rdd operations, and again, this is the part that I'm saying is very, very similar to your pandas methods. So there are two different sets of operations that we're going to briefly talk about: transformations and then actions. So transformations is basically something that changes your RDD. So map and flat map are the two main ones. Usually you want to use flat map, and map and flat map, that's what those are the methods that have Mapreduce embedded in them. So basically, if you have, let's see, this RDD that parallelizes these two pieces of data of hello world and how are you, using flat map and with a function like a lambda function, you will just perform that function across hello world and how are you. Of course, this list in the big data world will be like millions of strings of words long. But yeah, flat map is usually what you want to do, because flat map will, I believe, if I'm not wrong, map does it for a select subset of your data, whereas flat map does it for all. I might be wrong in that, but flat map definitely does the function on all. And then map does it for, I think you would select which ones to do map on. And then again, filter, you can do filters in the same way with a lambda. Let's say you only want to filter for things that are, I don't know, 3 words long, or yeah, 3 words or fewer. You can use the filter in the same way with a lambda function to do that. And of course, you can also define your own functions, because this is done in Python. You can actually define your own functions to plug into the lambda here. Similar to what a lot of you were doing with your pandas data frames with like the dot apply, the dot map, that kind of stuff. Works in a very, very similar way, just some of these methods are named differently. All right, so these are Rdd transformations. Other than that, there's also Rdd actions. So basically, actions perform operations that return a value after running some sort of computation on the RDD. So the first couple we talk about is basically like displaying our data frame. So first, rather than doing just outputting your data frame, you would use .collect to just return all the elements of your RDD. Take is the same as .head. So to do take like 5, you would return the first 5 rows of your RDD. And these I think are pretty self-explanatory. First element. Count gives you the total number of elements in the RDD. So why this is a computation is because your data set is being split up across multiple systems. And so when you're doing, getting the first, it has to figure out which one is the actual like first row of your RDD, because it is kind of like split up across your different systems in like a seemingly in like a random way. So it needs to figure out which was the actual first. So some aggregation does have to happen before you can get the actual first row of your data frame. Similar for count, like for count, you gotta probably, I'm guessing they would count up the number of rows on each separate system and then aggregate that together. And then, yeah, in a kind of similar way, the collect and the take, because your data is split up across multiple systems, some aggregation has to happen before you can actually return these results. So that's why these are a little bit more complicated than what's happening with just plain pandas data frames. Questions on these so far? In a similar way as to like I say that you don't have to memorize your pandas methods, you really don't have to memorize these. These are all like available if you like just Google what you need to do. I would say almost every pandas method has an equivalent with RDDs. All right. So use cases of Spark. Spark, again, has the bandwidth to work with big data. So a lot of people do use Spark or PySpark to stream and analyze data in real time as it's coming in. So you have your ETL pipeline set up, and ETL again stands for extract, transform, and load. So once you have this pipeline set up, and by pipeline, I mean like literally a series of functions to get your data from its raw format to whatever the format you need it to be for analysis. That would be like your data's cleaning steps, basically compressed into like one or a couple functions. And once you have that all set up, as data is coming in, it knows to feed the new data into your ETL pipeline, and then that can, I don't know, join the rest of your data in its clean state. Spark is also pretty good at doing data enrichment, which is the part that I talked about. As your new data comes in, you can combine that with the data that you already had. And it has some functions that, some architecture that's already set up that can do that for you. Something that's really neat as well, which is I believe one of your labs has you do this. You can also do machine learning within PySpark. And it actually is from the MLlib library within PySpark. So you can actually import that. And I think I have like a picture example later, and you'll see, I think I have a decision tree example, but yeah, you can do ML modeling. You can do things like market segmentation. You can run clustering algorithms, and also things like sentiment analysis and recommendation engines. And basically, you can also set up interactive analysis. So basically, as data is coming in, your, for example, your interactive dashboards will update all your visualizations. If you set it up in an interactive way, they'll be updated in real time. So you can see, like, let's say, I don't know, let's say suddenly you have a lot of like complaints about coming in on your app, you will get that information live. So interactive analysis. I think the next slide is going to be my last slide, just to show that you can do machine learning modeling, everything that we're doing in the last phase, you can do that within PySpark as well. So here you can see that the syntax is very slightly different, but same thing. You know, you are instantiating a decision tree model here. And I guess here you're also training the classifier. And then you can make predictions. You can find your, basically this is like doing a confusion matrix. And then also you can output whatever metrics are built into the decision tree objects here. So I will say like some of the names of like the attributes and the methods, like the .fit, .predict, they are going to be named different things here, but it's really just a matter of looking up the documentation to figure out how to do it. And I will say the more exposure you get to just anything in the data science world, the easier it will be to pick up all of these like adjacent things. So with that, does anyone have any questions regarding big data? Something that I also wanted to mention is that here I mentioned Hadoop and PySpark. These two are actually independent of AWS and like Amazon Web Services. So Hadoop and PySpark, I will say, are kind of, their popularity is going down because Amazon has, like, you know, if you have one service on Amazon, you might as well have all of it on Amazon, I think. So I know that more and more people are favoring to do all of these, not using PySpark, but using whatever Amazon has built that basically can do the same thing. So whether you learn PySpark or not, I mean, everything is a useful skill, I think. But whether you will need to use PySpark at your job, it really depends on your company. So with that, because there's so many different ways to work with big data, I think what's better to focus on are like the main concepts like Mapreduce, and maybe learning a little bit more about like the architecture and how RDDs work. I think those will be more beneficial if that's something that you want to work towards. All right, any questions to close out?
So Ish, do we need to, I know there's a couple, like, I think when you start to get into recommendation systems, recommendation systems in PySpark, is this something that we'll need to be able to do the other, like the other labs, I guess?
Yeah, that's a good question. I believe nothing else needs PySpark. I think it's just this one, just because the built-in methods for building recommendation systems in PySpark are easy to access. So I would say it's honestly optional. The recommendation stuff that I'm going to go through tomorrow are the new algorithms that there's basically one new algorithm that is commonly used with recommendation systems that I'll talk about tomorrow. But yeah, I would say not necessary. For this project and for next project, for your capstone, you don't have to use PySpark unless it's something that you really want to explore. I honestly think that it would take a lot of time. Unless you're already familiar with this field, I would suggest against it. But unless big data is something that you really want to work towards for your first job, out of bootcamp, then sure. But yeah, for now, I would say just know what PySpark is and how and like what it's used for, big
Okay.
data, and I think you'll be fine.
Okay. Got it.
Yeah. And I would say like in terms of career trajectory, data scientists, I feel like we have that, what's the word? The versatility of like data scientists are sort of in between, you know, the technical and the non-technical side of the company, just because we have to work with both, you know, like something that I always say for your projects is, are you able to explain this technical thing to a non-technical audience? Your presentations are geared towards non-technical audiences. And so you really have, you know, I guess you have the freedom of choice of, you know, do I want to get more and more technical and in the weeds, or do I want to go more towards like decision making, or like, yeah, like statistical decision making or model based decision making. So it's really up to you guys and whatever you find more interesting, which direction you go in. And I will say, yeah, like dealing with big data, you will want to get more other certifications if you want to grow in that area. Cool. Anything else?
This is just kind of a random question,
Mm-hmm.
but for like context, so a company like Netflix, they're using some sort of distributed system, and then they also have something like the Yarn on top of it, like PySpark, that's allowing them to like make these recommendations in like a point, like an interactive basis.
Mm-hmm.
Is that like how the flow for these bigger companies is set up?
I can imagine that like they have their product data, which is all of their content for streaming. That probably lives on like a bunch of servers, right? Imagine all of the videos that Netflix has available to stream lives probably, again, this is all hypothetical. I don't know how it's set up, but I can imagine it's on a bunch of servers. And then you have, you know, the people who are writing algorithms. These algorithms probably, yeah, I can imagine they exist on something similar to Hadoop. And basically, I can imagine that you can set up a connection between like Hadoop and those data servers. And so what Hadoop and like, if they're using PySpark, their data scientists or machine learning engineers can write algorithms and then have the algorithms be applied onto the data. And Hadoop is kind of like what will help make that connection between, you know, the algorithms and all of the data that Netflix has. Like if they wanted to write a recommendation system for like that will span across all of their content, I imagine that's like kind of a structure of what they would do. And like if they wanted to do something as simple as, let's say they wanted to like edit the titles of all of their movies in, I don't know, into like lowercase, for example. If they wanted to do something as simple as that, they would like have an executable function, have that be fed into like whatever it is, and the Mapreduce process would take all the data, not the Mapreduce process, but like you'll have all of your data, and it's a combination of Mapreduce and the distributed systems that will allow you to do this one simple process on all of Netflix's content. So it's kind of a, yeah, I imagine because they have so much data in storage, it's probably not in the same place. But yeah.
And then this is a random follow-up, but I've heard of like different podcasts they're talking about. There's kind of like the argument of all these segmented processes like we just talked about. And then there's something like Snowflake. That's like have you ever heard of those? They're like the cloud data platforms that have all of these steps in one platform. Do you like have any insight on that? I know that's beyond the scope of this.
Yeah, I actually have a friend who works for Snowflake, so I know a little bit. Yeah, but Snowflake and companies like Snowflake, another one is Datadog, and actually a couple of Flatiron grads have gone on to work for Datadog for sure. Snowflake, I don't remember, but yeah, these platforms basically are like an all-in-one, you know, like everything in one package. You can store your data in the same place, analyze your data in the same place, run models on your data all in the same place, versus something like Amazon. I am not sure if Amazon has something that allows you to aggregate all these steps, but Amazon basically has the way that I'm aware of that mid-sized to small-sized companies use Amazon is they just select their products and all the things have to have this line of communication between each other to work. Beyond that, I don't know too much about like the details of these and like what is preferred, where is industry going. I will say like there is the benefit of, if you have your data stored in different places, you have the benefit of like, if something goes wrong on one of your servers, it won't affect anything else. Usually like you have the, what's that called? Like shuffled backups, such that if like one server fails, you're able to still access that data because it's backed up on other servers. And that's definitely a benefit of like not having everything in one place. And I think similarly, like let's say Snowflake server is down. I don't know what measures they have in place, but if they didn't have any measures in place, all of their services would be down if their servers were down. Versus, yeah, it's like hedging your risk across multiple things. But take all of what I'm saying about this with a grain of salt. I'm no expert in this, in like the hardware, like big picture, like multiple tech stack field. I only do the data science part. Let's see, what else?
If we want to run the PySpark, we have to install the Docker, right?
Yes, so Docker is basically, they call it a container. And what that allows you to do is it allows you to have like a space in the cloud to work with PySpark.
I tried to install it, but I haven't the option Kitematic or something like that.
Okay, so Kitematic, it's a very, very recent thing that happens, which I know it's giving a lot of people problems in like the last couple of cohorts. So very, very recently, I think within the last like year, if not year and a half, Docker and Kitematic, I think Kitematic used to be something that you needed to run Docker, but now it is no longer. What I suggest you do, again, if you have like issues figuring it out, again, let me know, but I will also be taking the same steps you would take. If you search on Slack, on the Flatiron Students Slack channel, just search PySpark and you have a lot of like, you will basically see whenever anyone is asked a question about like installing PySpark. I was actually going through that yesterday just in case like anyone needed to debug. But yeah, if you just search PySpark on Slack, you'll see a lot of other people's issues that they run into with the solutions that other instructors have given them. So that would be like a quick way to figure out if you're running into a specific error or the Kitematic thing. I saw a couple things on there as well.
Okay, thank you. And I have another question about what is Kubernetes?
Kubernetes.
Yeah.
That's a great question. Kubernetes is it's something. Okay, I won't be able to answer this right now. I have to look it up. I forget. But Kubernetes works with Docker too. But I forget what exactly the function of Kubernetes is. It's something that I know that, if you have Docker running with or without Kubernetes, you won't have to worry about Kubernetes if you have Docker running. But I don't remember what it's used for, to be honest. Yeah, I'll look that up. I believe it's probably in one of these. It's probably in one of these, if not, yeah, it's something that runs with Docker, but I forget. I'll look it up and get back to you on that.
Thank you.
You're welcome. Anything else? All right, well, tomorrow we start on recommendation systems, and recommendation systems will be like the first of the 4 project topics that we're going through. So let me just go back to the home room so we can see that. Again, even though you might not do a recommendation system project, please come to the study groups so that you're aware of some of like the buzzwords or the lingo. That's going to be important. But yeah, same goes for all the other topics for like time series, image classification, NLP. Even if you have decided that you don't want to work on that, I feel like it won't hurt to just, have it just like be aware of some of the terminology that is used. But yeah, any final questions to close out?
What's the breakdown of like which topics fall into which topic, which sections fall into which topics?
Yeah, they're actually very self-contained. So if I open phase 4, and let's see, phase 4. Oh yeah, and I agree. The master-slave terminology has to be phased out. It should be phased out soon. Anyways, all right, the breakdown of topics. So recommendation system is its own topic. Time series are 37, 38. Natural language processing, I'm actually going to be talking about NLP over 2 study groups, but it's all in topic 39. I will be also touching on some of the stuff that is in the appendix under deep NLP. And then neural networks, you have to understand neural networks to get to image processing. Here, there's no image processing yet. And then only when we get to 41 is deep neural networks. And then this is also, 42 is also relevant to image classification because that's how you tune your neural networks. But yes, everything is pretty self-contained. All of the other topics, well, PCA and clustering are, I think, the only ones that don't fit into these directly. You can use PCA and clustering with any of these 4 topics. And then PySpark and AWS, they're just like working outside of your local environment.
Thank you.
You're welcome. Anything else? Cool. All right. If not, I will see you all tomorrow for recommendation systems. That's my favorite topics. I'm really excited. And if not, I will see you all at your project reviews, and have a good rest of your day, everybody.
Thank you.
You're
Thank
welcome.
you.
Bye.